Hello and welcome to today's lecture on battery driven system design. And here is the agenda of today's lecture. I shall give a brief background of this battery driven system design, particularly we shall emphasize on why battery driven system design is necessary. Then we shall discuss characteristics of batteries which are commonly used in modern embedded systems, and then we shall consider how the characteristics of these batteries can be modeled by using various techniques. Then we shall focus on battery driven system design, various approaches for this purpose, and battery scheduling and management approach, and battery aware task scheduling. We have seen that there is a strong proliferation of portable computing and communication equipment such as laptops, palm tops, laptops in recent years. In recent years, these battery operated portable systems are increasing at a very large, rapid rate compared to servers and other systems. And this growth rate of this portable equipment is very high. We have observed that. And one important characteristics of these batteries that not only where these systems is that not only the number of such equipment is increasing, battery driven systems are increasing, their complexity is growing. Let us focus on one of the most common portable equipment, that is cell phone. Initially, cell phone was developed primarily for voice communication. Now, we are using cell phone not only for communication of voice, for sending SMS, for accessing internet, for receiving radio, FM radio, for capturing picture and so on. So, the number of functions is growing, and as a consequence complexity of these devices is increasing with the use of with the rather increasing need for the users. And as these devices are battery operated, battery life is of primary concern. So, we find that battery is an integral part of these systems, because if the battery fails, the system fails. If the battery battery power is reduced, the capability of the system reduces. So, battery plays a very important role in these portable devices. Unfortunately, the battery technology has not kept up with the energy requirement of these portable equipments. That means, the energy requirement of these portable devices is increasing because of the increasing complexity of different applications, but the the energy that can be delivered by battery is not increasing at that rate. We shall have a look at the curve, plot of that later on. Then commercial success of these products depend on weight, cost and battery life. Since battery the battery dictates the commercial success of the products. Why? You see, the size of the battery will decide what will be the weight, and how long the battery will last, that will also decide the commercial viability of the product. That means, whenever you go for buying a laptop, you will demand that the between 2 charging it should sustain maybe 12 hours. Similarly, whenever you are trying to buy a cell phone, you will see that the weight is small, but it consumes much less battery, and these are that means weight, cost and battery. Of course, cost is another important parameter. So, what we can say that battery is significantly influencing the commercial success of these products. What is the alternative? The alternative is to develop low power design methodology, so that these products are become commercially viable. And as a consequence, a new approach has emerged, which is known as battery driven synthesis approach. That means, now you have to consider battery as part of your system design. Earlier, battery characteristics were not ignored. It was assumed that battery will supply power, it will supply desired amount of current maybe for certain duration. But if we use a battery driven system design, we shall see the life of the battery can be longer. That means, after you charge it, it will give you power for a longer duration. In other words, in some situations the life of the system will decide the battery life. For example, in sensor networks, sometimes the sensor networks are deployed in jungles. So, there is no way you can replace the battery or recharge the battery. That means, the battery with which it has been deployed will decide how long that system will work. So, battery driven system synthesis is very important, and we shall see how it can be done. I was talking about the widening battery gap. Here we find that the power consumption is increasing rapidly in modern systems. This is a little older data, but even in recent data the rate is increasing. That means, the complexity of these systems are increasing. As a result, this pink line, as you can see, which is representing the power consumption of battery operated systems, is increasing at a very high rate. On the other hand, you can see the energy density of batteries. That means, the energy density is represented by energy density is essentially represented by ampere hour is the the energy that can be stored in a battery per kg. That means, larger the weight, obviously the capacity will be more. So, per kilogram of battery, what is the energy that can be stored in the battery? That is how the energy density of a battery is represented. You can see the energy density is definitely improving with the improvement of technology, but their improvement is not really much. So, it has improved, but compared to the power requirement, it is much less. That means, the gap between the need and what actually can be supplied by the battery is widening with time. So, how this gap can be bridged, that is what we shall discuss. So, this particular diagram has been taken from a paper on battery driven system design, a new frontier in low power design by Kanishka Lahiri, Anand Raghunathan, Sujit Dey and Devashish Panigrahi. It was published in a international conference on VLSI design. So, now let us have a look at the different features of batteries that we use to characterize a battery. Number one is energy density, of which I have already mentioned. Number one is, that means, the ampere hour or per kg. This is a very important parameter, and this we would like to have this particular parameter to be improved. That means, we want larger energy to be stored in a battery of smaller weight. Second important parameter is life cycle life. What is cycle life? Cycle life is, as you know, these batteries operated are rechargeable. These batteries which are commonly used in these embedded systems are rechargeable. Question is, how many times charging and discharging can take place? For example, if you are using nickel cadmium battery, nickel cadmium battery can be charged and discharged maybe 4000 times. So, that means 4000 times the battery can be charged, and obviously it can be used when the discharge will take place. So, that decides the life cycle, and longer it is better. Then environmental impact. What is environmental impact? Environmental impact is, to realize these batteries, you are using some chemicals which may be toxic. For example, in nickel cadmium batteries, you are using cadmium. Cadmium is a very toxic material, and obviously, those nickel cadmium batteries are to be handled with care, and after the nickel cadmium battery becomes unusable, you should not discard it anywhere. You should carefully dispose it off, so that it does not go to the environment, otherwise it may be harmful to the to life. That means it has impact on the environment because it releases toxic material. Then safety. Safety is another feature which is very important, because how safe is the battery when you use it. We have read in the newspaper that a particular device, cell phone or some embedded system has exploded. How it has exploded? Actually, when the battery terminals, that means the positive and negative terminals, are shorted, some batteries will explode. That means, if you draw a very large current, it may lead to some kind of explosion. So, how safe is the battery? That is also very important feature of the battery. Then comes the available supply voltage. So, available supply voltage is another feature. Available supply voltage. You know that different batteries can supply different voltages. For example, the popular batteries that we use, those lead acid batteries, that can provide, I mean, per cell 1.5 volt, and similarly nickel cadmium battery will provide 1.2 volt. But our requirement in the system may be different. For example, when we are using a 5 volt supply, then you have to use several batteries to get that 5 volt or 12 volt or whatever it may be. That means, the voltage that is generated by the battery has to be taken into consideration, and that is your available supply voltage. And last but not the least is the charge discharge characteristics. Later on we shall see, whenever you will be charging a battery, you cannot really charge at a very high rate. That the charging rate is usually much smaller than the discharge rate. So, and also how the discharge rate influences the characteristics of the battery. These things are to be are very important whenever you go for battery driven system design. Now, let us have a look at some battery technologies which are commonly used. The most commonly used technology is nickel cadmium, which is matured and widely used in portable systems, in cameras, cell phones, and in many MP3 players and so on. It is popular, and it gives you high discharge rate. That means, it can supply large load current, and however, the limitation is that it has got low energy density. Energy density is small compared to other technologies, and as I mentioned, cadmium is a toxic material. So, it has got toxicity. That means, it is not very, I mean, safe to use. You have to use them very carefully. So, this is the characteristics of nickel cadmium batteries, which is one of the most commonly used batteries. Then comes the nickel metal hydride. Nickel metal hydride is also used nowadays, and it has becoming popular because of large energy density. So, energy density is very large, but unfortunately, the life cycle is very shorter compared to nickel cadmium batteries. That means, you cannot really use it for a long durations. The number of charging and discharging you can do is small compared to nickel cadmium. Then inefficient high discharge rate. That means, the discharge rate, the rate at which it can supply current to the load, is not very good. So, it is inefficient. Moreover, it is costlier than those nickel cadmium batteries. Nowadays, we are using lithium ion in most of our cell phones, MP3 players and other systems, primarily because of much higher energy density, longer life cycle. However, it is unsafe when used improperly. As I was mentioning, that lithium ion batteries, particularly when the battery terminals are shorted, it may lead to explosion. That means, you have to use them very carefully. And then the last one is a emerging technology, lithium polymer. It is very attractive because of smaller size, ultra thin, and larger energy density, and also it is safer, but unfortunately, it is not yet commercially very successful. So, it is a emerging technology. So, the most popular present day technology is lithium ion, the other technologies like nickel cadmium and nickel metal hydride are also used. Now, coming to the energy density of different batteries, as you can see, nickel cadmium batteries has lower energy density, that means your watt hour per kg for nickel cadmium is little more than 40. On the other hand, for nickel metal hydride it is more, it is close to 70, little more than 75, and for lithium ion it is maximum, it is little less than 100 watt hour per kg. And reusable alkaline batteries, which are not commonly used in portable systems, which were earlier used. Initially it gives you good energy density, but not as high as lithium ion. And that lithium polymer, which is a emerging technology, as you can see, it can give you 120 watt hour per kg, but this technology is not yet matured and not commercially available. So, we have to really use one of these three, nickel cadmium, nickel metal hydride or lithium ion, in our portable battery operated systems. Let us now have a look at the basic principle of battery discharge. We know any battery will have two terminals, one is anode and another is cathode. This corresponds to lithium thionyl chloride battery. Here, as you can see, you have the lithium anode and carbon cathode, and you can see you have a electrolyte in between, and then lithium ions go from anode to cathode whenever you discharge it. And so, the basic components are anode, cathode and the electrolyte, suitable type of electrolyte that you have to use. So, whenever you are doing the discharge, oxidation of anode results in generation of electrons, and that leads to flow of current between cathode and anode. This is how really the battery discharge takes place, and in simple terms. And whenever you draw more and more current, then more and more reaction sites are made unavailable as reactions proceeds. What happens as the currents are drawn, electrons flow, electron flow take place. What happens, these reaction sites gets covered by some material, and those surfaces become unavailable, and that is the reason why gradually the lesser and lesser surface area is available, and lesser current can be supplied by the battery after the initial charging. So, and again whenever you do the charging, then those reaction sites are made available to the user. So, this is how charging and discharging occurs in a battery. Now, let us now have a look at some of the electrical characteristics of the battery, because ultimately you will be using a battery and you have to look at the electrical characteristics, and these are some of the important electrical characteristics. One is your open circuit voltage of a fully charged battery. That means, after you charge a battery and if you do not apply any load, it will give some voltage. This is known as VOC, or that means the open circuit voltage. This open circuit voltage is usually higher than the nominal voltage. For example, those lead acid batteries, that is the typical voltage is 12 volt, can give you open circuit voltage of 13.5 or even 14 volt whenever it is fully charged and no load is connected to it. Then comes the V card, that is your cutoff voltage of a fully discharged battery. That means, after a battery is fully charged, and then if you start drawing energy from the battery, that voltage level goes down, and for example, a 12 volt battery, the voltage can go down below 11.5 or 11 volt when the charge is it has no energy stored in it, most of the energy has been discharged. So, this by measuring these voltages, you can give an approximate idea about the condition of the battery. You will find that in your laptop, if you click on the battery symbol, you will say that 75% energy is being stored. How that is given? Actually, it measures that that voltage, that means your that voltage across the terminal, and by measuring that terminal, it can tell that how much energy is presently available from the battery. So, and so far as the capacity is concerned, there are several types of capacity. Number one is theoretical capacity. So, theoretical capacity is the upper bound of energy that can be stored. That means, whenever a battery is being designed, depending on the weight, depending on the size, depending on the materials that is being used, theoretically one can calculate how much really energy it can be supplied. So, this is the theoretical capacity. So, usually theoretical capacity may not be same as the standard capacity. So, standard capacity is energy extracted under standard conditions. So, that means, whenever you are using the battery in standard conditions, what do you really mean by standard condition? Standard condition is that you have to maintain a particular temperature, you have to draw current at a particular rate, and based on that how much energy can be supplied. So, this standard capacity can be less than the actual capacity. Actual capacity is the amount of energy capacity that a battery delivers under a given load. That means, this actual capacity is the capacity of the battery that you get whenever you are actually using it. So, in that condition you have to take into consideration the thermal effect. For example, the ambient temperature can be low, can be high. For example, it has been found that the current delivery capacity of a battery is heavily dependent on temperature. Those who are using cars, they know that in most of the situation the car battery fails in winter. The reason for that is temperature is low at that time, and as a consequence the battery is not capable of giving high current. So, temperature effect has to be taken into consideration, and not only that, the current discharge profile, you are not really drawing a constant current from the battery, which is done in whenever you define standard capacity. Normally, you draw sometimes heavy current. For example, whenever you are starting a car, you are drawing very large current to start the motor. On the other hand, when it is running, battery is essentially not supplying much current. So, similarly in laptop, when you turn on the laptop, then it draws heavy current from the battery, and subsequently the current that is being drawn depends on the application you are running. So, you have a varying load, and under the varying load condition, varying current is drawn from the battery, and under this condition the actual life or actual capacity that we will get will be different from the standard capacity and theoretical capacity. So, from this we can really define the objective of battery driven system design. So, what is our objective? Our objective is to maximize actual capacity of the battery that will be drawn whenever you are using it in practice. So, maximize actual capacity by taking into consideration the characteristics of the battery. Okay. So, that is the goal of the battery driven system design, maximizing actual capacity. Now, as I was mentioning that charge discharge characteristics is also very important, and actually this happens because of these two effects. One is known as rate capacity effect. What is rate capacity effect? So, rate capacity effect is dependency between the actual capacity and magnitude of the discharge current is dependent on the rate at which the current is drawn. The reason for that is, as I mentioned, whenever you are discharging a battery, that the active area that is present in the battery will decide how much current it can supply. So, if you draw at a larger rate, obviously more area will become unavailable. If you draw at a slower rate, more area will be available I mean more active area will be available. So, when discharge rate is high, surface of the cathode gets coated with insoluble compound, and this prevent access of many active areas and consequent reduction in the actual capacity of the battery. And that is the reason why rate capacity plays a very important role in deciding the actual capacity. That means, if you draw at a slower rate, you will get longer actual, I mean larger actual capacity. Then another important feature is another characteristic is recovery effect. So, it depends on the concentration of the positively charged ions near the cathode. That means, the rate of diffusion is affected by this particular phenomenon. That means, concentration of positively charged ions near the cathode, that decides the I mean the charge, that means the current driving capacity. So, when heavy current is drawn, rate at which positively charged ions are consumed at cathode is more than supplied. So, that means, whenever you are using a battery and that time the positively charged ions available to you reduces. Now, if you keep the battery in ideal condition for certain duration, then again that positively charged ions will be available. It is a common practice, those who are driving cars, they know that suppose you try to start the engine, it may so happen the engine will not crank, it will not start. What the driver do? Normally they will find that they will switch off the battery and then wait for certain duration. What actually they are doing? They are unknowingly using this recovery effect. That means, the battery will recover, more and more positive ions will be available near the cathode, and as a consequence the necessary current that is necessary to start the engine will be available now. So, this is the recovery effect. So, these effects are to be taken into consideration in the system design to get larger actual capacity. Now, whenever you do this, you have to use a model of the battery. So, battery models capture the characteristics of real life batteries and to predict their behavior under various conditions of charge and discharge. So, that is the requirement of the model, and there are different types of model. Number one is analytical model. So, analytical expressions are formulated to calculate actual battery capacity and lifetime under different conditions such as variable and constant load. That means, it takes care of the charge discharge characteristics, and based on that it can find out that if you draw this much of current, if this is the initial charge, and after drawing this much current at this rate, this will be the charge left. So, this type of equation is provided in the analytical model. So, it captures the rate capacity and the thermal effect. So, it also takes into consideration the impact of temperature, that means thermal effects, and but not recovery effect. So, analytical model cannot take care of the recovery effect. So, Peuckert's formula which is represented by Q is equal to k by I to the power alpha. So, this simple formula was proposed by Peuckert to model the battery, where K captures the electrochemical effect. That means, battery is essentially a electrochemical device, and those electrochemical effect has to be taken into consideration, and those are taken care of by this parameter K. And for different batteries, the value of K will be different, and alpha represents the rate capacity effects. That means, as you draw the I to the power alpha, where alpha is the takes care of the rate capacity effects. That means, as you discharge the battery at a particular rate, then the charge that will remain present, that can be obtained from this. So, analytical models are a simple way of modeling battery, and there is another type of model based on electrical circuit model. So, in this case, model battery discharge using an equivalent electrical circuit, that is a SPICE model. So, in this particular case, you can really consider it as if it is a electrical circuit, and you can by using SPICE model the you can represent the characteristics of the battery, and in this particular model is capable of modeling rate capacity and thermal effects. Then coming to the third model, that is known as stochastic model. So, in this case battery is represented by a finite number of charge units, and the discharge behavior is modeled using a discrete time transient stochastic process. So, this is a little complicated technique, but this can take into account variable loads, rate capacity and recovery effects, but not thermal effects, and particularly in this case computation requirement is modest. Coming to the last model, that is your electrochemical model. So, this models electrochemical thermodynamic processes. So, it takes into consideration the physical construction, what is the length, what is the width, what is the thickness, and various materials used and so on. So, actual physical dimensions are taken into consideration, and this can analyze many discharge effects under variable loads, including rate capacity effect, thermal effect and recovery effect. And obviously, these electrochemical models are most accurate, but computational intensive. That means, it will take a long time to perform computation. So, later on we shall see out of these 4 models, analytical models are more commonly used in our analysis, and later on we shall see how it is being done in some applications. Now, I have discussed about some of the important characteristics of these models. So, based on this, how do you really design battery driven system I mean how do you perform battery driven system design? There are several approaches. Number 1 is frequency scaling. So, information from a battery model is used to vary the clock frequency dynamically at runtime using workload characteristics. We have seen that that rate capacity effect, we have that rate capacity effect tells you that if you draw with a smaller current I 2 compared to I 1, then you get more actual capacity. That means, if you draw at a smaller rate, you get longer life or larger actual capacity. So, how do you really draw smaller current? As we know, based on the workload condition, you can find out what is the frequency at which a particular system can run. So, you can reduce the frequency, and as you reduce the frequency, the power requirement for the system will reduce, it will draw smaller current. We know that because that power dissipation is proportional to CL VDD square F. So, if you reduce F, the current will decrease, and as a consequence it will give longer actual capacity. So, you can do frequency scaling. So, to take care of the workload, and based on that you can get longer life of the battery. Then you can do supply voltage scaling, as I have already discussed. Select VDD to find the best trade off between the battery capacity and performance. So, what you can do, depending on the workload condition, you can do voltage scaling. So, if you reduce the voltage, as we can see here, if you reduce the voltage, the current that will be drawn will be reduced, and as a consequence you can match the current drawn with the workload condition, and that in turn will lead to lesser current and longer actual capacity and larger battery life. Then we can do dynamic power management. So, in this particular case, the policy that controls the operation state of the system according to the state of charge of the battery. That means, what can be done? So, if we find that the charge is getting depleted, you can, as to take into account the recovery effect, we can switch off some of the subsystem for certain duration, and battery will recover. Again you can turn it on. That means, you can do what is known as power management. So, you can shut down, turn on, and you can give required recovery time for the battery to get more actual capacity. Then we can do battery aware task scheduling. This tailors the current discharge profile to meet the battery characteristics. So, I shall discuss some technique for that. So, battery scheduling and management, as I was mentioning, efficient management of multi battery systems. Nowadays, sometimes we do not use a single battery. You can have multiple batteries in a system, and whenever you are using multiple battery in a system, for example, you will find that when high reliability is necessary, instead of using single battery, you will be using multiple battery, and those batteries need not be uniform of same type. The batteries can be of different types. So, in such a case, what you can do? You can do static battery scheduling. So, there are different ways of doing it: serial scheduling, random scheduling, and round robin scheduling. That means, say suppose you have got 4 batteries. So, use battery 1 for certain duration, then you can you switch over to battery 2, and in the meantime battery 1 will recover. Then after using battery 2 for certain duration, you can use battery 3, and after using battery 3, we can go for battery 4, and so on. In this way, you can do it serially, one after the other. Serially means after battery 1 is completely exhausted, you will go to battery 2, then battery 2 will be exhausted, then you will go to battery 3. So, this is the serial method. On the other hand, round robin is, you are using it for certain duration, the battery is not yet fully exhausted, then we will switch to battery 2, again use it for certain duration, it will not be fully exhausted, then you go to battery 3. In this way, you will be doing, say, battery 1, then battery 2, then battery 3, then battery 4, then battery 1. So, in this way it will be, or you can say, will come back to this. So, in this way you will be doing using the battery in a round robin fashion. So, whenever you are using this the batteries in round robin fashion, obviously each battery will get enough recovery time, and as a result actual capacity will increase. Then terminal voltage based battery scheduling. So, here makes use of the state of the charge of the battery. Suppose you have got 4 batteries. So, it may not be necessary that it may not be true that all the batteries will have equal capacity. So, it may depend on how old is the battery, whether how much what is the actual capacity of the battery, I mean how much discharge has taken place of a particular battery. By that I mean different batteries will have different energy stored in it. So, you can take into account that by measuring the terminal voltage. That means, accordingly you can schedule the batteries, instead of making it round robin. The battery which has large capacity, you can use it more than a battery which has less capacity. So, in this way you can do a more intelligent scheduling based on the state of the charge of battery. Then discharge current based on battery scheduling, use heterogeneous batteries with different rate capacities. That means, you can have different batteries which can provide different current efficiently, different amount of current efficiently. So, depending on the workload, you can select a particular battery which matches the discharge profile of that application. So, in this way you can have discharge current based battery scheduling or battery efficient traffic shaping and routing. So, network protocol, for example, nowadays battery driven systems are battery operated systems are used in communications, sensor network and many other applications. So, their network protocols and communication traffic patterns play an important role in determining the battery efficiency and lifetime. So, in that case, depending on the network protocol that is being used and the communication traffic pattern, that means that is inherent in the system, that can be used in determining the battery efficiency and lifetime. So, in other words, I mean to summarize this, what I can tell, you can do suitable scheduling and management to get to maximize the actual battery capacity and longer life of the entire battery system. Okay, coming to the last topic, that is battery aware task scheduling. So, here as I mentioned, the objective is to maximize the battery lifetime, and the various characteristics which you would like to use is rate capacity effect, and a higher rate of discharge leads to lower available capacity, that is known, that has to be used. Then recovery effect, the battery voltage recovers in idle periods, that we know. So, that has to be used. Another feature which has been observed, that is known as non-increasing profile. So, non-increasing load sequence leads to lesser drop in voltage. I shall discuss it in more detail. This has been taken from a paper entitled Static Task Scheduling Algorithm for Battery Powered Dynamic Voltage Scheduling System. So, this was published in IEEE Transactions on VLSI System, and the paper was by Prince C. Chaudhuri and Chaitali Chakraborty. So, in this paper they have utilized these characteristics of the battery, and then they used dynamic voltage scheduling, and this is that rate capacity effect that I was mentioning. For example, here the battery is supplying for 400 milliampere, and the task will run for 6 minute. So, this is in minute, 6 minute 400 milliampere. So, a particular task requires that, and whenever this is done, then 30.9% voltage drop take place, and after 11 iterations of this. So, this is when you are discharging at a very high rate. Then you can do voltage scheduling, and if you do the voltage scheduling, then you can reduce the current. Obviously, the actually it will not be voltage scheduling, voltage and frequency scheduling. As you do that, then the current can be reduced, but the execution time will increase as I have mentioned. So, energy drawn from the battery is same. So, 8 into 300 is same as 6 into 400. However, in this condition 26.9% voltage drop occurs, and after running this, and it survives 14 iterations instead of 11 iterations. That means, it can, this task can run 14 times compared to 11 times in this particular case. Similarly, whenever further voltage and frequency scheduling is done, scaling is done, the current can be reduced to 200 milliampere, and obviously, the execution time will be 12 minute. So, in such a case 22.7% voltage drop occurs, and this will survive 16 iterations. And finally, you can reduce the voltage and frequency in such a way, the current drawn is 100 milliampere. Obviously, it will take longer time to execute the task, that is 24 minutes, and the voltage drop is 18.7%, and it will survive 17 iterations. So, you can see you are getting much larger actual capacity. Instead of running the task 11 times, you are able to run it 17 times, and because of you are getting larger actual capacity. So, you are drawing same energy, but the actual capacity that you are getting is more. So, that is the rate capacity effect. And another feature that I mentioned, that is your non-increasing profile. So, suppose you have got 4 tasks to be executed, and duration of each of them is mentioned 7 minute, 5 minute, 8 minute and 10 minute, and these are the deadline times. So, after meeting the deadline times, you can schedule them, and which have different currents. As you can see here, the scheduling has been done, where the task which draws larger current has been scheduled first, then the task which draws next higher current is scheduled second, then the third one is the next the which draws lesser current than the first two, and finally, the task which draws minimum current is scheduled. So, this is your non-increasing profile. So, you can schedule it in this way, or you can schedule the other way, where the task which draws minimum current is scheduled first, and then in a increasing order you schedule the various tasks. And obviously, whenever you schedule these tasks in this manner, your the deadlines are not violated. So, both will serve the purpose, but you can see the voltage that is present, that is analytical Q, in case of that is present in the system in the non-increasing profile is 31724 and compared to non-decreasing to 26145, and terminal voltage is 4.04. That means the battery is in better condition, or rather battery has got more charge, which is represented by this compared to the next situation. So, 3.94 is lesser voltage. So, the voltage drop in the first case is 23.6, in the second case is 32.4. So, this shows that non-increasing profile, this non-increasing profile means you are decreasing the current discharge is better in battery operated systems. That means, initially the battery is in good condition. So, it has larger current drive capability, and as you keep on using it, lesser and lesser active area is available. So, it is better to schedule in a non-increasing profile. So, you can use these three phenomena: rate capacity effect, then recovery effect and non-increasing profile effect. Using them, they developed this paper. They have presented a task scheduling algorithm, and they have shown how the actual capacity is increasing. And the battery model that was used is a analytical model. Instead of using this simple model Q is equal to k by I to the power alpha by Foucault, they used a little complicated battery model, and this actually takes care of variable current, and on the other hand, for constant current this reduces to this particular expression here. Alpha is equal to this alpha, where is y alpha beta, this is the alpha. So, alpha reduces to this in case of your constant current. So, this particular Maddeley model was used in that paper. So, subsequently some of my students work in this area. They developed another approach, and here a set of task graphs, each with task in the task graph specifying the start time, execution time and deadline time, and current loads was provided, and the algorithm work in two phases. An initial earliest deadline first base schedule is done, and then in the second phase selection of an optimal pair of supply voltage and body bias. So, in the previous paper what they did, they used only dynamic voltage scaling. So, that it reduces only the dynamic, it takes care of the dynamic power. So, in this particular work not only dynamic power reduction, but leakage power has been taken into consideration. So, reduction of leakage power takes place by using body biasing, and as I said, there are works in two phases. In the first phase, initially an earliest deadline first base schedule is made, provided the task dependencies are not violated. Then the task schedule is modified by scheduling the task in non-increasing order. As you have seen, non-increasing order gives you better result of the current loads, provided the deadlines and task dependencies are not violated. From the first task check, if the battery fails at a task, then some modification is done. Then they downscale the failed task to minimize voltage and check again. If the battery survives, then check the deadlines. If the deadline fails, then they repeat the same production procedure with previous task. If this goes on till the last task, the deadline and goes on till the last task and deadlines fail, then the battery fails to schedule. So, there are situations where a battery will fail, but in situations where it does not fail, we get a schedule, and that schedule is used in the second phase. In the second phase, it takes the schedule obtained in the end of phase 1 as input, starting from the last task. So, here we are starting the last task. So, you have scheduled task 1, task 2, task 3 in this. So, you start with the last task, and the slack obtained at the end of the task is utilized to get optimal pair of supply voltage and body bias. That means, slack is being used to do the scheduling, to use supply voltage scaling and body biasing. They are combinedly done such that the reduction in power dissipation, there is maximum reduction in power dissipation. So, minimum current is drawn from the battery. then this procedure is followed until either there is no more slack or further scaling down is not possible. So, the output of the second phase is a schedule that maximizes the battery lifetime without violating the deadlines. So, and here is some experimental result. So, these are the tasks, these are the execution times and various deadlines, and these are the currents which is being drawn. So, schedules were done without dynamic voltage scaling and reverse body biasing. So, the energy consumed is 177.07 joule, and when only dynamic voltage scaling was used, as in the first paper that I have shown, there is significant reduction. You can see energy consumed is only 26.62. So, percentage reduction in energy 84.96, but whenever we use dynamic voltage scaling and reverse body biasing as it is done in the second paper, then you can see the energy consumed is much less, 12.76, and reduction in energy is 92.79%. And moreover, there is some technology dependence. As we know, the leakage current increases or static power dissipation is more in smaller dimension technology. So, some experimentation was done by varying the average duty cycle of the task profile for two different technology generations. So, with using 0.18 micron technology, the modeling was done. So, the first line, that red line on the top is without dynamic voltage scaling and without reverse body biasing. Then if you use reverse body only dynamic voltage scaling, you can see there is significant reduction in the energy consumed whenever the duty cycle is small. So, duty cycle is 10%, 15%. As the duty cycle increases, that means the less and less idle time is available, then you can see the energy consumption reduces, and when 40% duty cycle is there, then it becomes, I mean, that means there is no idle time when you can do dynamic voltage scaling. So, then the energy consumption becomes same as without dynamic voltage scaling and reverse body biasing, and you can see with reverse body biasing there is a more reduction in energy. And in case of 70 micron technology, you can see the energy consumed is much more because leakage current is much higher, and there is substantial reduction by using reverse body biasing. So, this is with dynamic voltage scaling, that green curve, and the lower curve is using reverse body biasing. So, you can see with reverse body biasing the current consumption is very small, energy requirement is very small up to 25% duty cycle, and as the duty cycle increases, that means idle time reduces, then there is lesser scope for dynamic voltage scaling and reverse body biasing, and energy consumption increases. So, and actually on running 100 task profiles with varying percentage of task, this is the result that we get, and the two curves, for one is with this is percentage reduction with dynamic voltage scaling only, and this is using dynamic voltage scaling and frequency scaling, and with reverse body biasing. So, we find with 70 nanometer technology there is a big gap between when you use dynamic voltage scaling compared to when you use both reverse body biasing and dynamic voltage scaling. So, from this we can conclude that as the duty cycle increases, the utilization increases, the reduction in the energy consumption also decreases because of lesser available slack, and as the process technology further gets lower, the energy due to static power becomes insignificant, and the algorithm using reverse body biasing has become more efficient. So, with this we have come to the end of today's lecture. So, we have seen how you can take into consideration the characteristics of the battery to prolong the battery life by increasing the actual capacity of the battery. Thank you.